This project looks at how prosthetic legs move during walking using basics, physics, and dynamics. We studied things like motion, force, torque, and energy to see how the prosthetic works compared to a real human leg. By doing with this, we hope to improve how comfortable, safe, and natural the prosthetic legs feel for the user. We also looked at both bases and boarded prosthetic to understand how they respond during different walking phases, like stance and swing. We studied how an artificial leg works while walking. We looked, we looked at both regular and boarded prosthetic legs. We used simple diagrams and energy formulas to study how they move. We focused on things like how much torque is at the joints, how inside parts are built, how strong the motor is. This helps show how using physics and motivation studies can solve a real medical problems. Why study dynamics in biomedical engineering? Because this makes it easier to design prosthetics that move like real legs. We understand how the body moves. We can build limbs that feel natural and help people walk better. Good design means less pain, more balance, and more comfortable for the user. Prosthetic legs need to help people walk by moving like real legs. We use motions and force idea to study how the legs should move and how to build the joints. If the design is wrong, it can cause bad balance or even hurt the person.
During the swing phase, the prosthetic limb is off the ground and moving forward. Here we used angular motion equations to calculate its velocity and acceleration. Why is this important? Because its values determines how smoothly the limb can match the user's natural gait. If the timing is off, it could cause imbalance or discomfort. So by analyzing the phase, we make sure the prosthetics moves in sync with the user's step. In the stance phase, the limb is on the ground, bearing the user's weight. We use a free body diagram to analyze the forces acting on the knee joint. Newton's second law helps us calculate the ground reaction forces. They tell us how strong the joints need to be supported to use safely. It's a key step in making sure the prosthetics doesn't feel under load and provides enough stability during walking. This slide focuses on how much torque is needed to rotate the limb. We use the formula, where I is moment of inertia and alpha is angular acceleration. Calculating torque helps us decide what kind of motor to use, or how to design passive joints that don't make the user tired. If torque is too high, walking becomes harder, so this step is essential to comfort and efficiency. Here, we looked at how much power a motorized prosthetics needs for each step. We calculate it using torque and angular velocity. This helps in selecting the right motor and planning battery usage. If power requirements are too high, the battery drains quickly. So understanding this tells us how to make the limbs more usable for longer periods, especially in real-time, everyday conditions. Efficiency tells us how much of the input energy becomes useful motion. We used the formula. Lower efficiency means energy is lost, maybe through heat or intentional resistance. In real life, a higher efficiency prosthetic means fewer battery recharge and smoother working. So this analysis helps us design limbs and last longer and feel better for the user.
Let's start with the power requirements in motorized limbs. These limbs rely on actuators, typically electrical motors, and that must generate like enough torque to mimic human movements. To do this efficiently, we calculate the energy demand based on the limb's weight, the user's gait cycle, and required joints. For example, powering a knee joint for walking may need around 30 to 60 watts, depending on the speed and load, battery life, and motor efficiency. Become critical in ensuring the limb uh, can function all day without recharging. In prosthetics, efficiency is calculated as output over input power, multiplied by 100%. This tells us how much energy is actually used for motion versus how much is lost, typically due to internal resistance or heat. High efficiency is crucial because powered limbs rely on batteries. The more efficient the system, the longer the device lasts between charges, and the more reliable it becomes for the user. Okay, so here are some key quantitative results from our analysis. The limb achieved a velocity of 2.7 meters per second and an acceleration of 1.8 meters per second squared. Torque applied at the joint was 2.16 Newton meters. Input power was measured at 7.62 watts, resulting in an output of power of 6.48 watts. Additionally, we calculated a ground reaction force of 352.3 newtons and a moment of inertia of 1.08 kilogram meter squared. These figures confirm that the prosthetic limbs perform within realistic ranges for daily activities like walking. Okay, so how do these values relate to real-world function? Every dynamic calculation, whether it's velocity, torque, or force, contributes to both safety and comfort. For example, how quickly the limb accelerates affects walking smoothness. Design decisions must reflect how these variables interact. A minor change in torque can affect ground reaction force, which can affect balance. By understanding these dynamics, we ensure that the limb can perform effectively in practical everyday situations. Kinematic implications. Kinematic focuses on motion, especially the timing of limb phases like swing and stance. If swing phase timing is off, it can cause limping or imbalance. That's why we fine-tune velocity and acceleration to simulate natural human gait, when done correctly, the user experiences more stable fluid movement, which improves both comfort and mobility. Force response and structural design. Finally, we assess the force response and structural strength of the limb. The calculated ground reaction force confirms that the prosthetic can support full body weight during motion. Structural design ensures the joint, especially the knee, won't fail under repeated loading. We also optimize the limb to handle varied terrain, improve stability, and reduce the risk of falls or joint damage over time.
For mechanical effort and energy use, let's start with the mechanical aspect first. When the prosthetic limb requires higher torque, when more power is needed, whether it comes from an electric motor in powered limbs or the user's own muscles in passive ones, this increases energy consumption and in turn leads to faster battery drain or physical fatigue. That's why torque optimization is crucial. It directly improves performance while reducing strain on both the system and the user, which is very important. Now, why is efficiency such a big deal? A more efficient prosthetic means fewer battery recharges, smoother and more natural movements, and longer component lifespan. But beyond the technical benefit, it also means better day to day convenience and comfort for the users, which is the most important thing. Ultimately, efficiency isn't just a design goal, it's what makes limbs truly usable and reliable in real life. Going over the limitations, of course, we know that no model is ever perfect. In our analysis, we assumed the ideal conditions, which means we didn't account for things like, for example, soft tissue behavior or changes in weather or how real users move. For future work, we could incorporate motion data from actual users, use sensors for adaptive feedback, and simulate more realistic conditions with advanced materials and biomechanical models. Looking forward, here are some enhancements that could really level up the prosthetic performance. First, smart sensors that detect and adapt to terrain in real time. So, for example, if you were in a more harsher climate, it would adapt to that specific climate immediately. Next, using a lightweight composite material to reduce bulk and improve comfort. Then integrating energy efficient motors to extend battery life. This is essentially important for people that love to spend time outdoors. And finally, adjustable joint damping, which helps tailor the prosthetic's responsiveness to the user's needs. Not only does it help with comfort, it also helps with the wear and tear of the prosthetic. In conclusion, dynamic isn't just math, it shapes medical solutions. This project helped us apply engineering principles to real devices that restore mobility. It reminded us that behind every calculation is a person whose life depends on a good design.